notation and standard series. Lesson 3. H2 Mathematics. Writing out 1 plus 2 plus 3 all the way to 2026 is tedious. Mathematicians are famously lazy, so they invented a shorthand using the Greek letter sigma, one compact symbol that says add all these terms up. By the end of this lesson, you will read and write sigma notation fluently and evaluate sums without listing every single term. The sigma notation has 3 parts. Above the sigma is the upper limit, n. This is where we stop. Below the sigma is the lower limit, r equals 1. This is where we start. And to the right is the general term, f of r, the function we are summing. Note that r is just a dummy variable. We could equally use I, k, or x. Example 1. Write 1 plus 2 plus 3 all the way to 2026 in sigma notation. This is an arithmetic progression with general term UR equals R, starting at R equals 1 and ending at R equals 2026. So the answer is sum from R equals 1 to 2026 of R. Example 2. Write 3 plus 9 plus 27, and so on up to 2187 in sigma notation. This is a geometric progression with common ratio 3. The general term is 3 to the power of r. To find the upper limit, we solve 3 to the k equals 2187, giving k equals 7. So the answer is sum from r equals 1 to 7 of 3 to the r. A common misunderstanding: confusing r cubed with 3 to the r. R cubed gives cubes, 1, 8, 27, 64, and so on. 3 to the r gives powers of 3, 3, 9, 27, 81, and so on. They only share the value 27 at r equals 3. These are very different sequences, so be careful. There are 3 key properties of summation you need to know. First, the constant multiple rule. You can pull constants out of the sum. Second, the sum and difference rule. You can split the sigma across addition and subtraction. Third, splitting bounds. To sum from m to n, take the sum from 1 to n and subtract the sum from 1 to m minus 1. Let us work through an example. Evaluate the sum from r equals 1 to 20 of 4r plus 5. Using the sum and difference rule, we split this into 4 times the sum of r plus the sum of 5. For the sum of r, 20 times 21 over 2 equals 210. Multiply by 4 to get 840. For the sum of 5, we add the constant 5 20 times, giving 100. The total is 840 plus 100, which is 940. A very common mistake. Students think the sum from r equals 1 to n of 5 is just 5. But we are adding the constant 5n times, so the answer is 5n. With n equals 20, that is 5 times 20, which is 100, not 5. Evaluate the sum from r equals 10 to 20 of r. We use splitting bounds, sum from 1 to 20 minus sum from 1 to 9. That is 210 minus 45, which equals 165. Why do we subtract up to r equals 9 and not r equals 10? Because the r equals 10 term must be included in our answer. If we subtracted up to 10, we would remove it. Here are the 4 standard series formulas. The sum of a constant k from 1 to n is nk. The sum of r from 1 to n is n times n plus 1 over 2. These two must be memorized. The sum of r squared and the sum of r cubed. These will be given in the exam if needed. Evaluate the sum from r equals 1 to 10 of 3 to the r plus 2r plus 5. We split this into 3 separate sums using our properties. For the sum of 3 to the r, recognize this is a geometric series. First term a equals 3, common ratio, r equals 3, and n equals 10. Using the GP sum formula, 3 times 3 to the 10 minus 1, all over 2. That gives us 88,572. For part 2, 2 times the sum of r from 1 to 10 equals 2 times 10 times 11 over 2, which is 110. For part 3, sum of the constant 5 10 times equals 50. Adding them all together, 88,572 plus 110 plus 50 gives us a total of 88,732. Sometimes the function does not match a standard form directly. We can use a substitution to shift the index. Given the sum of r cubed formula, evaluate the sum from r equals 1 to 100 of r minus 1, all cubed. Let k equal r minus 1. Then when r is 1, k is 0. When r is 100, k is 99. The sum becomes sum from k equals 0 to 99 of k cubed. We separate the k equals 0 term, which is 0, and the remaining sum from k equals 1 to 99. Applying the standard formula, 99 times 100 over 2, all squared. That is 4,950 squared, which equals 24,502,500. We could also expand r minus 1 cubed into r cubed minus 3r squared plus 3r minus 1, and use linear combinations of standard series. But that requires the sum of squares formula and is much more tedious. Index shifting took us just 3 lines. The expansion method would take 8 or more. Always look for the elegant approach. Quiz time! What is the sum from r equals 1 to 15 of 3r minus 2? Is it A, 315, B, 330, C, 345, or D, 360? Take a moment to work it out. The answer is B, 330. We split 3 times the sum of r minus the sum of 2. 3 times 15 times 16 over 2 is 360. Minus 15 times 2 is 30. 360 minus 30 equals 330. Quiz 2. Given that the sum from r equals 1 to n of ur equals n squared plus 2n, find u5. Is it A, 9, B, 11, C, 35, or D, 25? Remember the key formula, un equals Sn minus Sn minus 1. The answer is B, 11. We use un equals Sn minus Sn minus 1. S5 is 5 squared plus 2 times 5, which is 35. S4 is 4 squared plus 2 times 4, which is 24. U5 equals 35 minus 24, which is 11. Option C, 35, is a common trap. That is S5, not U5. Let us recap what we have learned. Sigma notation is compact writing for sums. Sum from start to end of f of r. We covered 3 key properties: constant multiple, sum and difference, and splitting bounds. The standard series formulas let us evaluate sums quickly. Remember, sum of a constant k is in k, not just k. Index shifting is a powerful technique when the function does not directly match a standard form. And un equals Sn minus Sn minus 1 lets you find individual terms from a given sum formula. 5 key takeaways to remember. 1. The sum of a constant c is c times n, not just c. 2. Number of terms equals upper minus lower plus 1. 3. Recognize geometric series hiding inside sigma notation. 4. Index shifting is often simpler than brute force expansion. 5. Un equals Sn minus Sn minus 1. Lets you find individual terms. In our next lesson, we will cover the method of differences, a powerful telescoping technique for sums that do not fit standard formulas.